Hello, everyone. Good morning. Welcome to discussion 11. We'll be talking about graphs and graph algorithms today. So I'm aware that Professor Aman has not covered all of these yet. And as such, some of them I will just briefly mention and skim over until so that you can go over it with Professor Aman in more detail. It's going to be a little hard for me to explain it anyway without his input. So as always, if you have any questions, go ahead and ask. We will have a Menti, but the Menti will happen at the end of the presentation. So you better take notes if you want to win a virtual rubber ducky. And there will be a participation quiz at the end of the discussion, as always. So if you missed any of the discussions before, you can still get that extra credit because you need only 10 quizzes. Before I start, do you guys have any questions for me about the previous topics, about what Professor Aman covered in his classes, about the projects, even though we will be doing project reviews or project overviews for you guys? If there are no questions, okay, Olivia. So the project in general, the project in general is a little confusing, and you will have to a lot of times flip the way you think about it, or flip the way the calculations are going to work. The information I can give you right now is that there is a good document made by Julia, the TA, about it's basically her solution for the example given in the project specifications. The way to go about it is we advise you guys to have 3 kinds of maps in your project. The first map takes in the key, or the key is the string, the link string or the website string, and the value is a vector of websites that point to the key, not that key points to. You want the vector of values that point to the key. And these values in the vector can be strings. It doesn't matter because you can have 2 more maps that store the same keys, but the values are the rank and the out degree of the key. And those 3 maps you can use to keep the calculations going. I will advise you to revise the matrix multiplication. That is going to be important. If you're not comfortable with that, definitely look it up. There are plenty of resources online. You can always reach out to us too. We can help you out with that. Because you will not be able to use a matrix. You will have to use the adjacency list. And thus you will have to be very comfortable with matrix multiplication and how it works to be able to apply that to a list as opposed to having a matrix with placeholder zeros. If you have any further questions about the conceptual understanding of the project, reach out to any of us. About Dijkstra. Okay, Brody, I will actually go over that in detail in this presentation, and I will have an example that showcases exactly how you find the path, how you find the distances, etc. So to keep on going with the algorithms, Today, we're going to cover the shortest path algorithms. So that's going to be Dijkstra and Bellman-Ford. We're going to cover minimum spanning tree. So we're going to cover Prim's and Kruskal's algorithm. And you will, Jesus Christ, you will learn about the complexities of all of these, the properties, and how to perform them, both on paper and you will be given some pseudocode for writing these. So shortest path algorithms can have either the single source or, well, you will mostly be focusing on single source shortest path algorithms, although it can be different slash you can have various implementations. The ones that we're going to cover, such as Dijkstra and Bellman-Ford, are the single source shortest path algorithms, which means that they're looking for a shortest path originating from a single vertex, and it visits all the other vertices. So the first one that we're going to talk about is the breadth first search. The complexity of the breadth first search is of V plus E, where V is the number of vertices and E is the number of edges in the graph. You are familiar with this one because we covered it before. This can be applied to unweighted graphs only. The second algorithm is the Dijkstra algorithm. Its complexity is, it varies depending on what kind of implementation you have. It can be either OV squared, or if you use a heap for it, it can be O of V plus E times log V. And as always, V is the number of vertices in the graph and E is the number of edges. This algorithm can be applied to a weighted graph. So if you want to use graphs in your final project, I want you guys to remember these properties and apply them to your problems. I want you guys to think, is my graph going to be weighted or unweighted? Which algorithm will be the best for it? Another property of Dijkstra's algorithm is that it cannot handle negative weight edges. For that, you will have to use something else. And that something else is the Bellman-Ford algorithm, which has the complexity V times Z. We're familiar with what V and E are. Bellman-Ford algorithm can handle the negative weight edges, and it can detect negative cycles, but it cannot handle them. It cannot do anything with them. It cannot calculate the paths properly. It cannot give you the correct solution if your graph has negative cycles. And I don't think we have any algorithm for you that will handle the negative cycles. And I don't think it's realistic to have such an algorithm anyway. So Dijkstra's algorithm, it's a single source. It determines the shortest path to each vertex from a single source. It works on weighted graphs with no negative weights, and it can be used on directed and undirected graphs. So whichever one you have, it'll work on both. It is a greedy algorithm, and a greedy algorithm means that at each step, at each iteration, the next step is determined by the best outcome. So if you think about visiting vertices, at each vertex, the next vertex that you visit will be determined based on the shortest weight. So if you have, like, I don't know, if you have 3 nodes coming from, or 3 vertices coming from the one that you're at currently, this one's the current one, you will decide whether you want to visit 1, 2, or 3 based on these edges. So you will look which one's the smallest, and then you will go there. Okay. Now, so another thing that happens at each iteration is the relaxation principle, which I will talk in detail later. It is applied to all the edges that originate from the current node, so the unvisited vertex that has the minimum distance to the source vertex. So the one that you're looking at, the one that you're observing, it relaxes all the edges that originate from that vertex. And the time complexity is O v squared, or if you use a heap and adjacency list, it's going to be v plus e times log v. So relaxation or edge relaxation principle is it looks at an edge and checks whether the path through vertex u to vertex v is better than any previously found path to vertex v. So it's a fairly simple comparison. It updates the distances or distance map, however you want to store the distances, for the key v to be the distance from the source to u plus the distance from u to v if that's shorter. So if your dv in this case is if your dv is the current shortest path to key v, it will check this condition. So if the path to u plus the weight from u to v is shorter than the current distance to v, then it will update the current distance to v to be the shorter value of the two. If not, it's just going to keep the old one. Algorithms for the shortest paths usually solve the problem by repeatedly using the edge relaxation in certain order. And you'll see that the Bellman-Ford actually relaxes all the edges at all times, every iteration. So Dijkstra's algorithm, the variant that we have has basically 3 maps or a table with 4 columns. The map with that tracks vertices that are visited, so it's a V map. Each vertex is a key, and then a value is a Boolean, which states whether or not that vertex has been visited. A distance map, which stores all the distances from the source node. So each key is a vertex as before, and the value is a distance from the current key to the source node. At the initialization, all of these distances are set to infinity because Dijkstra prefers the smaller values. And so you want something very, very large to be the initial value so that it doesn't interfere with the performance of the algorithm. The source vertex distance value is set to 0, and that way it is selected first when you read the map. And then the third map is the predecessor map. Each vertex is a key as usual, and the value is the last vertex pass through to arrive to the key vertex. It's essentially the node that gets you to that vertex. And all values are initialized as null. This specific map is used to find the shortest path from the source vertex to any vertex. And it's usually used in as a pair with the distance map. The way you could do this in and you don't care about the predecessor map if you're just looking for the shortest distance, not the exact path, but just the distance. You don't care about the predecessor map. So once again, think about what you need, what kind of properties you want, what kind of calculations you want, and then implement any of these. It's giving me all the... Okay, here we go. Now I'm going to run through the algorithm for you guys in this example. The initialization stage, we have the 3 maps. So the first map is the key and the visited vertex. The second map is the key and the distance to the key. And then the third map is the key and the predecessor of the key. If you want to implement it as, if you want to program Dijkstra's algorithm, you could have 3 separate maps, or you could have this be an object or a class and have all these properties for it. All of these properties as fields, and then you have a one map that has all of those. So we are starting with S. That's going to be our source node. All of these are set to false. Distance at S is 0, so we select that one first, and the other distances are infinity. And then all of the predecessors are null. Once we visit S, we set the visited value to true, and we look at the edges that go out of S, because this is the directed graph. If it's an undirected graph, you look at all the edges that connect to S. So we put these values into our table. S connects to T, so we're gonna put distance to T to 10 and the predecessor to T to be S. And then S also connects to Y, so we put the distance to Y to be 5 and the predecessor to be S. Between these two, because this is a greedy algorithm, we will choose Y to visit, because at each step we choose the best outcome. So 5 has a small, 5 is smaller than 10, so Y has a smaller distance away from S, so we will choose that one. So we visit Y, set the value of in the visited map to true, and keep these. So you want to keep these distances because you will be reusing them. You will be at each stage using all of these. Now, Y has 3 edges coming out to the other nodes. It connects to T with the weight 3. So that means that the total path from S to T, if you go through Y, is 5 plus 3, which is 8. So you update that value to 8 and set the predecessor to be Y, because 8 is less than 10, which we had previously. Y also connects to X with an edge with weight 9. The total distance from S to X is 14, so you put that in your table. And same with Z. The total distance from S to Z is now 7, and the predecessor of Z is Y. Out of all of these values right now that are unvisited, the smallest one is 7. So we're going to visit Z, set that to true, and the predecessor is going to be locked in as Y. Now we observe the edges coming out of Z. So we have 7 to S. We don't want that. S is already visited, so we don't care about this one. And we have 6 to X, which brings the total path from S to X to have the weight 13 when you add all of these up. When you look at all of these values now, we have 2 that are unvisited, T and X, and between those two, T has a smaller value. So you pick that one to visit, and its predecessor is Y. So instead of going to from Z to X, you're gonna go to from Y to T. So you visit this one, you were visiting T, set that one to true, and then you do the same thing. You look at the edges. We visited Y, so we don't care about that one, and there's weight 1 from T to X. So we update that in the table, and right now that's the smallest value left. So we visit that one. And that's basically the end of that's how you fill out the table. And I'm gonna also show you how to read the table later. Do you have any questions at this point? Are you all clear on the on Dijkstra and filling out the table? If there are no questions, I'm gonna move on. So this is a little pseudocode for you guys, or just like an explanation of how to write the code. So you initialize V with all the vertices and mark them all as unvisited. You initialize distance with the source vertex distance set to 0 and all the others to infinity. and then the predecessor map to all values set to null. Now, while V has unvisited vertex, so that while the map V has any value that is false, you find an unvisited vertex U that has the minimum distance value in the distance. So you pick the minimum from the distance values. And at this stage, this is where you can do the optimization using a heap, because you can use a min heap for that. And at that point, accessing this minimum distance will always be of 1. Mark that U has been visited in V, and then for each U's edges, you store the distances, you add them all up, and then you relax the table for Y if necessary. So you check if the new path from U to Y is going to be shorter than the previous path that we had from source node to Y. And then you keep repeating that. So here's a question that that is going to come up on the exams, on quizzes, etc. It is asking you to find the path, the shortest path between S and X using the table that has been filled out using Dijkstra's algorithm. So in this table, we don't have the visited column, but we have the distance and path. So because the entire Dijkstra's algorithm has been run, which means that all of these are the minimum values already, we just have to read the path in reverse from X to S. So you read X, to get to X with the shortest path, you need to go through T. To get to T with the shortest path, you have to go through Y. And to get to Y with the shortest path, you have to go through S. And that's our source. So the path is then reversed, S, Y, T, and the X. And that is the solution. The correct one. Yeah, you're correct, Andrew. So essentially, the easier way to do it is to backtrack from the final node and just read the predecessors. Now, negative edge weight. Dijkstra's won't find the optimal solution in a graph that has negative weights because of the greedy approach. So if you have negative weights, it will always prefer the negative weight over the positive one because it will give a smaller sum. And it doesn't necessarily mean that it's gonna, like, if you look at this one, the path still has the absolute value of 10. And if you think about the weights as cost instead of distance, Dijkstra's algorithm will give you a path that costs more just because its cost is negative. Even though you'll have to think about tolls, you'll still have to give out that 10. So negative weight cycles, a cycle with a negative weight cycle is a cycle that when you look at its edges, the total weight sums up to a negative number. So no shortest path algorithm can handle negative weight cycles. And this makes sense if you think about weights as cost instead of distance. But the reason we cannot handle the negative weight cycles is because you will keep just going back and forth in this cycle. You will not visit any other nodes because of the negative weight. You'll just keep moving on in the cycle. Bellman-Ford. Bellman-Ford is a little slower and more complex to build, but it's a lot more versatile than Dijkstra's because it can actually handle negative edge weights. And not only can it handle negative edge weights, it can also detect whether you have a negative weight cycle in your graph. So it uses a distance map like Dijkstra's, And as I mentioned before, it relaxes all the edges at each iteration. So it performs exactly v iterations. And at each ith iteration, it finds the any source to destination, I think, path with I edges. And then the last iteration reveals presence of the negative weight cycles. The order in which you relax the edges can and will affect the performance. And I want you guys to remember this. This is important. So your implementation, i.e. the order of the edges here that you visit, will change the way you perform or the way your algorithm performs. So how it works, we have these three edges. They do not form a cycle, or we have these three nodes with three edges and they do not form a cycle. We have a table that has the distance and the predecessor. So just like in Dijkstra, so we're gonna start visiting the edges that we have. The first edge listed is edge from T to Y, even though our source here is S. So we check that one. It's negative. It's not only large, but it also doesn't have the connection to S, so we don't do anything with it, but we still have to visit it. And then the next edge is S to T, and we put that in the table, S to T, and weight 5. And then we do the same thing, S to Y, weight 2. And then at second iteration, you do T to Y, but T has been visited now. So you can add this edge and it will change the distance to -5 from S to Y. And then you do S to T, S to Y, and it keeps these values. The reason why you keep performing the iterations even though you've run through all the edges is because of the T to Y edge not being actually added in the table at the first iteration, because we haven't visited T yet. Now that we have, you add that edge into the table and its values, and then you also update the table. Yes, David, you will need an edge list for this algorithm. And then you also run through all the other edges too to check if maybe the original path that you had is shorter than the one that the newly obtained path. And then the final iteration checks for the negative weight cycles, and this iteration does not make any updates to the table. So no relaxation. And it does, and in this case, it didn't determine that there are any cycles. Here is a pseudocode for it. So you need to initialize the graph and map. And then this is the step 2 and step 3, which is the relaxation part and the checking for negative weight cycles. Do we have any other questions about this before I move on to minimum spanning tree algorithms? If not, I'm going to move on. So minimum spanning tree is a subset of edges of a connected, weighted, and undirected graph that connects all the vertices together without any cycle. So it forms a tree, which you are familiar with. And on top of making a tree, so no cycles, and connecting all the vertices together, it also does that with the minimum possible total edge weight. So once you connect all of these, the total weight will be the smallest of all the possible combinations. Two MST algorithms that are quite famous and we will cover are the Prim's algorithm and Kruskal's algorithm. and they're both greedy algorithms. A minimum spanning tree of a graph is not necessarily unique. It will be unique only if the edge weights are unique. So if you don't have any weight duplicates, the MST will be the unique. If you do have duplicates, you might have multiple possibilities for finding a minimum spanning tree. So Prim's algorithm, once again, connected, weighted, and undirected graph is necessary for it. The time complexity for an adjacency matrix is O v squared, because you have to technically visit every edge. And in an adjacency matrix, you have v squared values for edges. And if you have an adjacency list and a heap, it will be O of E times log V, log V for sorting and E for, or heap operations, and E for the number of edges in the adjacency list. Now, the way Prim's algorithm works is you create an empty set, which means that you will not have any duplicates. And you put an arbitrary node in the set. So whichever one you want, we're going to start with A. While your set does not contain all the vertices in the graph, and because sets have unique values, you can do that by checking if the number of vertices in a graph is the same as the size of the set. You keep adding the adjacent vertices with the smallest edge, adjacent vertices from the vertex that's already in the set, mind you, and the vertex that is not already in the set. And set will already do that for you, but if you have a set of pairs that stores the vertex and the distance to it, you might have to check for the vertices specifically. So example, we start with A, we add it to the set, and then we check the adjacent vertices. We have B and C. B has a smaller distance from A, so we add B. And then we check the rest of the values. We have B to C is the least weight, as opposed to A to C, which has 6. So we add C with the edge from B. Then we check the rest of the weights. The minimum one here is 6 that is unvisited, because we have 9, we have 6, and we have 7 accessible to us. So we pick the B to D edge, and then when we look at the remaining edges, we have 6, 9, 7, and 4. So we're going to pick the minimum weight edge, which is going to be D to E. Now the set has all the vertices, so you are done. Kruskal's algorithm is similar, but first of all, it picks the least weighted edges that do not form cycles. It works with edges as opposed to vertices. So because you have to check for the cycles, because Prim's algorithm excludes that by removing the duplicate vertices in the set. The time complexity of Kruskal's algorithm is E log E, which is, I think, different than what they said in the previous one. No, this is Prim's, sorry. So E log E, the limiting factor, or what slows down this algorithm, is the sorting of the edges. And yeah, so you'll see that here. The way Kruskal's algorithm works is that you need to work with an edge list, first of all. And the second is that you create an empty set of edges. Then you create a list of edges that is sorted by the least weight, hence why it's slower. And then while all the vertices are not connected by the edges in our set, you keep adding the least weighted edge that does not form a cycle. And one way to do this is the union find. So if you look at the example that we have, you need to create a sorted list of edges. And in this case, it's going to be A to B, because that's the shortest one. Then we have B to C, D to E, A to C, B to D, and then it's going to be B to E and C to D. And then we start adding the edges. The first one is going to be A to B, and then the next one is going to be C to B or B to C. It still doesn't form a cycle. And then the next one is going to be D to E, doesn't form a cycle. And then the edges that are left are A to C. A to C will form a cycle, so we skip that one. B to D, so we add that one because it doesn't form a cycle. And at this point, we have connected all the edges, so we don't have to keep looking. The good thing about this one is that you just keep looking at the first edge that you created, and you keep popping them off as you use them or as you add them to the set. Now we actually have the Menti time. The Menti code is 68511525, and I'm gonna share the presentation with you guys. Here we go. All the questions will happen at once, and then afterwards, if you have any questions, I'm gonna answer them. Okay, so question number 1, which of the following statements is not correct about Dijkstra's algorithm? And then the answers are: Dijkstra's algorithm uses a greedy strategy. The input graph can have negative weight edges. Dijkstra's algorithm is a single source shortest path algorithm, and the input graph can be undirected or directed. And yeah, that is correct. Let's see. You guys are correct. The majority of you are. The Dijkstra's algorithm cannot handle negative weight edges. It is a greedy algorithm, and it is a single source shortest path algorithm. It starts from a single source that you pick and picks the best or the shortest weight at each stage. Next question. Given this table, which is the same table that I used before in that example that I explained, what is the shortest distance between S and X? It is the same problem, so you can follow the same application for reading the tables. Yeah, that is correct. So if you look at the table has already been fully updated, fully filled out by Dijkstra's algorithm. So all you have to do to find the shortest path between X and S is read the value stored in the distance map. Next question. Oh, actually we have a leaderboard to because we're done with Dijkstra. Whoever this is, Geo, good job on taking the lead. Now, next question. Bellman-Ford. Bellman-Ford is able to find the shortest path in any graph with negative edge weights, true or false? And okay, so the thing is, while Bellman-Ford can work with graphs that have negative edge weights, it cannot work with any graph with negative edge weights, because a graph that has cycles, yes, exactly, Brody, cannot be read with Bellman-Ford. It cannot, the cycles can be detected, but you cannot find the shortest path. Next question. What is the minimum number of iterations in which Bellman-Ford could converge to its ultimate solution? So that means that there are no further updates to the distance map. And once again, as a reminder, Bellman-Ford, it really depends on what order of edges or what order you visit the edges in. And the solution is 1, as you've seen in the example that I ran through in the presentation. If we didn't start with that first node, with that first edge being the -1, or the -1, we would be done by visiting the other 2 first on the first iteration. That is one of the unpredictable, like it can be positive or negative when you think about it for this algorithm. So leaderboard, Brody taking the lead. Good job. Good job. I'm proud of you. Y'all are doing great. Who is ChatGPT? Who is ChatGPT? I hope you're not using ChatGPT for these questions. I'd be very upset. Next question, and these are the last 2. You cannot use Prim's algorithm to find the MST of a graph with which of the following properties? Remember what Prim's algorithm, what properties of graphs Prim's algorithm can handle. So Prim's algorithm can handle the cyclic graphs because it will just not add duplicate vertices. So once it reaches the cycle, it will just not add the last node of the cycle. It can handle weighted and connected graphs, which we've talked about, and it handles undirected graphs only. Directed graphs cannot be handled by Prim's algorithm. Next question. Huh? Or was that it? I think that might have been it. No, there is more. There's more. Good job, bro. No, there is another question. I don't know why it skipped it. Let me stay with me, guys. There is another question for you. There we go. There we go. What is the minimum spanning tree of the following graph? And the minimum, the answers are given as edge pairs or vertices pairs as an edge list. So minimum spanning tree, you can follow any algorithm that you want. No, I didn't share the participation quiz code yet. I will do it after the Menti. Yeah, this is the correct solution. You can run through any algorithm and it will most likely give you the same spanning tree for this one. Now, I'm going to share the code for Brody. You still took the win. Good job. I'll find a virtual rubber ducky for you.